Hi everybody, welcome to another video in Math 1324, section 8.1, sample space, event, and probability. So we go to the new chapter, the last chapter of the class about probability. So this is a very basic fundamental probability. Most of the calculation we can just refer to this very simple basic concept. And when we get there, I'll let you know. But first, we have some terminologies here. A random experiment is a process or activity which produces number of possible outcomes. So let's say we're flipping a coin, then we have head or tail, a head or the tail. So that is an experiment. You have outcome of getting a head or outcome of getting a tail. So that is a random experiment. Produce number of possible outcomes. And then we have the sample space. The sample space is the list of all possible outcomes. That's very important. We did that. And that list must be mutually exclusive, meaning they have no overlapping, and must be exhaustive, meaning they have to have all possibilities, not overlapping. So we count everything once and have to count everything. An event is a subset of sample space. Event is a subset of sample space. So let's look at some example. We have the experiment of flipping a coin. The outcomes are head or tail. In that case, the sample space could be head. Sample space will be either head or tail. We list all the possible outcomes, two outcomes, a head or tail. Right. So that is a sample space. Next, a random experiment rolling a die. So if a die is 6 faces, has 6 faces, each has number of dots. So we have 1 to 6 dots, and we're rolling. And the sample space will be either 1, 2, 3, 4, 5, or 6. So we have one of those 6. So that's why we list every possible outcome of getting a 1, 2, 3, 4, 5, or 6 in the sample space. And then some event. We can say an event is a subset of this. So we pick some of this. For example, even number could be 2, 4, or 6. Or number that is greater than 4, 5, or 6. So an event is a subset of sample space. We choose some of the samples, some outcomes in the sample space to be in the event. Right, let's look at some example here. If we have 2 fair coins are flipped, write the sample space for the experiment. 2 fair coins, right? So the first coin could be head or tail. The second coin could be head or tail. Now, that for each coin. Now we put 2 together. It will be like this. We can have head. Let's say the first one is head, and then the second one can be a head, or the second one can be a tail. Now, if the first one is a tail, the second one can be a head or could be a tail. So this is the sample space, all 4 possible outcomes. I would say S for sample space. But the way we list this will be usually like this. We have the first one, we can draw that is a tree diagram. For the first coin, we can have a head or a tail. On the second, we can have a head or a tail. A head or a tail for the second. So in that case, we have head, tail, head, tail. That's one way to list that. Another way is we list from right to left. The second, we have head, tail. The first one, we just repeat every 2. Tail. Right, we'll revisit this in a bit. But as far as sample space, this is it. Right, next, a fair die is rolled and a fair coin is flipped. Write down the sample space for that experiment. So a fair die have 6 faces, so we can have 1, 2, 3, 4, 5, or 6. and then a fair cone will have head or tail. Right. So we're going to pick one out of 6 here, which one out here. So let's say we may have 1 in head and then 1 in tail. Then we have 2 in head, 2 in tail, 3 in head, 3 in tail, 4 in head, 4 in tail, 5, 6. So the number is for a number in front will tell us the outcome for a die, and the second letters represent the outcome for a coin, could be head or tail. So we list all of that. I've got the 6 here and then 2 here. So select one of this, select one of that. So we have 6 by 2. 6 times 2, so that's 12 possible outcomes. Right. Next we define probability of an event. So probability of an event, there are 2 types of probability. So they're theoretical. Theoretical is where we're using probability theorem assumption and reasoning process, and empirical, so that is by experiment. Right. So let's look at the empirical first, and we usually don't do this in homework problem. So we said, suppose that we determine the probability of flipping a coin. In theory, a fair coin has give us 50% head or 50% tail. That's a fair coin. However, the coin may be not be fair. Suppose that we have a particular coin and we flip it, and by the way, flipping a coin is tossing that in the air, and whenever it lands, the head or tail is not like, this is not just flipping a coin, just flip it. Or we can do it like this, just spin it, and whenever it lands, it will be head or tail. And I can tell you that if we do that, it will not be 50-50, because technically a coin, the weight on 2 different sides are different, because the sides are different, so the weight are different. So when it rotates, the heavier side will tend to land lower to the ground. So in that case, usually the heavier side will land. And in that case, it's not going to be 50-50. So if you toss it in the air and you catch it in the air, it's more likely that you have 50-50 chance. But if you spin it on the desk like this, the chance to get that 50-50 is difficult. I don't want to see fly out the camera screen. But anyway, so let's say we have 100 times and 45 head and 45 tail. Find the probability of getting a head. So we have 45 of a tail out of 100. So that's 45% or for 0.45. Probability of getting a head, we have 55 over 100. That's 55%. Or 0.55. So, like I said, that's based on the experiment. We don't usually do that. In theory though, theoretical probability, first we have assumed that it is equally likely outcome. That is very important assumption. The probability of getting an event is the sum of the probability of the simplest event. Pretty much number of event in an outcome over the number of event in the sample space. So number of outcome in an event over the number of outcome in sample space. So this is equal to number of outcomes in an event over number of outcomes in the sample space. if we can count, we can do probability pretty much. Look at first example. A number is selected randomly from the list. So that is the sample space. So when we have this list, the sample space has 10 number. Find the probability that the number is divisible by 3. So we write down in the event E is divisible by 3. So what number in this list that are divisible by 3? We count 3, 6, and 9. Those are divisible by 3, and there are 3 of them. So with that we say the probability of getting this event of divisible by 3 is equal to how many we have in the event over how many we have in the sample space, and that gives us 3 over 10, 30% or 0.3. Of course, the answer can be fraction, decimal, or percent, whatever you want to write. Right, so there's fundamental probability, how many we have in the event divided how many we have in the sample space. Right, next. A fair coin is flipped 3 times. Find the probability of getting 2 heads and 1 tail. So, the first coin be head or tail. The second coin could be head or tail. And the third coin could be head or tail, head or tail, head, tail, head, tail. Now we just list how many we have in the sample space. Right. Head, head, head. Head, head, tail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. And tail, tail, and tail. So that is 8. Right. Actually, there's a, if we're going to list that in column, you will see. I'm going to write all the outcomes again. Head, 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 tail, head, head, tail, head, tail, head, head, tail, tail, tail. I just want to skip a line. Tail, head, head, tail, head, tail, 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 head, and tail, tail, and tail. Notice that if we look on the right, you have alternating head and tail. If you look on the one next to it, this is alternating, but for every 2. Head, head, tail, tail, head, head, tail, tail. And we look on the left, it will alternate for every 4. 4 heads, and 4 tails. So that pattern continues. If there's another coin, will be alternating every 8 heads and 8 tails. Right, so we have 8 here. Right, now for an event here we have 2 head and 1 tail. So event, we have 2 head and 1 tail. So let's just count how many we have here. 2 head and 1 tail. 2 head and 1 tail. 2 head and 1 tail. So there are 3 of them. Let's list. And there's 3 of them. So then the probability of getting this event of 2 head and 1 tail is 0.5. we have 3 over 8. Right. How is 3 over 8? 0.375 or 37.5%. Right, so it's like that. So we count how many we have in the event, divide by how many we have in the sample space. Will be just like that. Right, now this is a bit more complicated. Suppose there are 2 fair dice. It's tossed. Find the sample space. Well, that would be a lot. So there's 6 faces on the die. So you have 1 or 6 on the first roll, or first toss, and then you have toss the coin again, so we make another 6. So you have 6 on the first one, 6 on the second. So if we form a tree like this, there will be a tree first that have 6 branches, and then for each end there will be 6 branches again. So 6 by 6, 36. So we have 36 outcome here. So the way we list them is as said, this is the first coin. The first could get 1, 2, 3, 4, 5, or 6. So we said 1. The first coin is 1. Second, first could be 2. Let's just finish this first. And then 4. 5. Then 6. And now we have the second coin. 1, 2, 3, 4, 5, 6. We could have 1 on the second, 2 on the second. Just do that. Then 5. Right. And now that we have on 36 outcomes. So we decide to give the answer in the table like this. And they'll say, what if we have 3 dice? Well, if we have 3 dice, we cannot use a table like this, because for each die we have 1 dimension. If there's 3 dice, we have to have like 3 dimensions. So instead of a table, it's going to be like 6 tables on top of each other. Anyway, so we have 36 outcome here. So this is the sample space. We're not going to write this again. We say this is sample space. And there's 36 of them, because 6 by 6 is 36. Now, find the probability that the sum of the die is 7. So if we call the event of the sum of the die is 7, that be E. We're going to list out the case when we add up to 7. Right. 1 and 6. Just write like that. 2 and 5. Pretty much everything on this diagonal. 3 and 4. 4 and 3. 5 and 2. And 6 and 1. Those are the cases where the two numbers add up to 7. And there are 1, 2, 3, 4, 5, 6. So there's 6 choices here. So the probability of getting event is going to be 6 over 36, which reduces to 1 over 6, and 1 divided by 6 is about 16.7%. I'll just say 0.1666 repeating. Find the probability that the die is greater than 10. Now the E is greater than 10. The event of greater than 10. Greater, not equal to. Greater only. So the maximum we can have 6, which is 12. So greater than 10 could have to be 6 and 6. 6 and 5 is 11. But after that, there's none. So pretty much, as you see, everything on the diagonal have the same sum. So all of this add up to 2, all of this add up to 2, to 3, all of this add up to 3, and so on. The diagonal here add up to 7. So event greater than 10, we have to have only 5 and 6, 6 and 5, or 6 and 6. Those are all the possible outcomes that add up more than 10. And there are 3 of this. So the probability of getting the event is going to be 3 out of 36. Reduced by 3, we have 1 over 12. Or 3 over 36 is that. Or if we want fraction, we hit math and convert that to fraction. 1 over 12, right? So that. Or 8.33% if you want to. Find the probability that you will win the game when you roll a fair die first time and you get a higher number on the second time. This is more difficult, right? So let's say if you roll 1, if you roll first and you get 1, then if your opponent roll 2, 3, 4, 5, or 6, will win. If you roll the first one is 2, then the opponent will have to roll 3, 4, 5, and 6. So in that case, if you have, I'm just gonna take, sorry, have this. No, wrong one. Right. If you look at this case, below here, the second number is greater than the first number, right? The diagonal here we have the first and the second are the same. Below that, you have the second greater than the first. And that is where you lose the game. Wait, what do we want? We want to win. So the first number have to be higher than the second. So, sorry. Right. Look at that. Now this is where the first number is higher than the second. Right? Which is above the diagonal. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 of them. Right? 15 cases where the first die is greater than the second. So in that case, we have the chance of winning. You have 15 outcome of winning. And so the probability of winning is how many we have over the total of the sample space. We have 15 over 36, which reduced to and convert this to fraction. 5 over 12. Right. So think about this. There's 36 outcomes. There will be 6 outcomes in the middle. 1, 1, 2, 2, 2, 3. So this is where we draw, right? We have a tie. There's 6 cases. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. 6 outcome that we draw with the opponents. So 36 total. Take out 6 that you are draw. That 30 left. 30 events. 30 outcome left. Again, 36 total. 6 of them will be tied. Throw that away, you have 30 left. 30 outcome left. And on those, half of that will be winning, half of them will be losing. So 36 total, subtract 6 that are tied, 30 left, half of them, which is 15, so 15 of the chance you win and 50 of chance you lose, and that over 36 total. That's what we have. And then some properties of probability. A probability cannot be more than 1 or cannot be negative. So it could be 0 is the lowest number, 0, when that is impossible for it to happen. And then we have 1, that is certainty. So if probability equal to 0, that's impossible to happen. Probability equal to 1, it is certain. And we have to have everything in between. And if it is a simple event, or a simple event is the event only have one outcome in it. So pretty much the probability to get each of the outcome all add up has to be equal to 1. Right. And with that, we finish the first section in chapter 8. As always, thank you for watching and see you in another video in Math 1324.